Hello everyone. Today we'll talk about the right way to calculate the free space path loss. I'll show you that in two different Wi-Fi environments, the 2.4 and the 5 gigahertz. This is the equation, how to calculate the free space path loss. As you can see, it's equal 20 log D. D here is the distance, loss is the free space path loss, and D is the distance in kilometers. And it depends, if you want the distance in kilometers, you have to use the factor here 32.44, or if you want the distance in miles, then the factor will be different. It will be 36.6. That's why I have here two numbers to show you. It depends on what you prefer to do. And F obviously is the frequency, and I'll show you examples how we can apply how we can calculate the FSPL in 2.4 gigahertz and in 5 gigahertz and the difference between them. And the GTX, that's the transmitter gain, that will help to offset the loss or the free space path loss, and also the receiver gain. So as much as the gain, as much as the offset for the loss. So the better gain, the better loss. Let's put it this way. And an opposite, for example, the bigger the distance, the bigger the loss. Obviously, as you can see from the equation, is very straightforward, very simple to implement. The higher the frequency, the higher is the loss with the distance. So the longer the distance, the higher the frequency, the bigger is the loss. And that's why I said in previous videos that the Wi-Fi environment in 5 gigahertz is worse compared to the 2.4 gigahertz, and especially when you are dealing with bigger coverage. For smaller coverage, you prefer to use the 5 gigahertz because it's offer better speed, but then for bigger coverage you probably want to use the 2.4 gigahertz compared to the 5 because it has better lower loss, and we'll see that in the next slides. So in visual terms, here is a better diagram to explain these parameters. So you have a transmitter and you have a receiver. So as this is the transmitter gain, which is the transmitter gain of the antenna, and it is usually measured in dBi. For example, 18 dBi or 10 dBi. Depends on the antenna you use, depends on the manufacturer, depends on the other factors. And same thing for the receiver gain. Depends on the supplier of your antenna or manufacturer of your antenna. The distance between the transmitter and the receiver and the frequency used. So let's understand here what this really means a loss. Loss means that you lost in the amplitude of the signal. So here on the left side I show you a sine wave signal, and it shows you a dotted line, the original transmitted signal, and then the solid line is the received signal. And the difference in amplitude between the original signal and the received signal is called loss, and that's measured probably in power. And you can see this using oscilloscope. And another view, you can see the power loss of the signal in frequency domain, and you can see that easily if you have a spectrum analyzer. And you can see the dotted line on the top is the peak amplitude at the transmitter, and then the solid line is the peak amplitude in frequency domain at the receiver, and the difference is the loss in power. And that's why that's a result of a RSPL. So here I will show you a real examples how we calculate the free space path loss on 2.4 gigahertz environment. Here I pick 3 channels in 2.4 gigahertz, and these are the most popular channels, as you can see, channel 1, 6 and 11. And the reason that we pick these channels because they don't overlap, and they are very popular when you try to design a Wi-Fi coverage in 2.4. You would like to use these channels because they don't overlap between each other, so reducing interference. So that's why today I picked these 3 channels. Now we will examine these 3 channels across different distances. And here what you see in blue is 0.2 kilometers, which is 200 meters, 0.5 kilometer, which is 500 meter, 1 kilometer, and 2 kilometers. Now you see in 200 meters you have lower loss compared to the 500 meters, obviously, because the distance is shorter. So you have lower loss, probably around 84 dB or something, or 86 dB, I can't see exactly. But if you go longer distance, if you go from 200 to 500, then you do not double your loss. Like, your loss does not double. What happens is your loss will be worse by 8 dB. So from 200 meter to 500 meter, if you are broadcasting on the same channel, then your loss will be worse by 8 dB, and that's not a small number, because each 3 dB you probably kill your received signal by half. Now if you go from 500 meters to 1 kilometer or 2 kilometers, then it will be almost a steady state of 6 dB each time that you double your distance, and that because of the logarithmic curve of the free space path loss. Now if we look at channel 6 and channel 11, they behave the same in similar way. So you will have a lower loss in 200 meters, 500 meters, but then your loss will increase by 6 dB each time you double your distance. Now let's look at the 5 gigahertz, and I pick here in 5 gigahertz a few channels, which is the 40, 149 and 161. So currently as I'm speaking, I'm using the 149 channel in 5 gigahertz. And the impact on the free space path loss on the 5 gigahertz is obviously much worse compared to 2.4 gigahertz. So that's why 5 gigahertz is not a good band to be used for bigger coverage of Wi-Fi. If you need bigger coverage, you better use 2.4 gigahertz. But 5 gigahertz can offer a better performance in smaller coverage, better speed, more bandwidth, and you can use a carrier aggregation on 5 gigahertz because you have abundant of bandwidth and channels. You can aggregate between the channels and offering very high speed. Unlike the 2.4 gigahertz, which is relatively crowded, and you can't really pick very clean channels. You will always have interference because the 2.4 gigahertz is very popular, very crowded, not only by Wi-Fi access points, but also by appliances, sensors, and many other applications that use the unlicensed band. So I hope that this video helps you. If you have any question, please don't hesitate to comment on the video. Thank you.